All right, so yesterday we were graphing square root functions, and we started with our parent function, and then we did vertical stretches and shrinks, and vertical reflections, and vertical shifts. Today we're going to add in a horizontal shift, and then we're going to combine all of our different transformations into one big problem. And the only thing you have to remember is the order to apply them in. Otherwise, everything's exactly the same. You just got to know what order to take the steps in. So let's start with a horizontal shift. The first thing we want to do, the first thing it's often helpful to do, is to start with our parent function. Luckily, I saved mine from the last lesson. Boom, there it is. Sorry, maybe I should say whoop, there it is. But I said boom, so not quite as good. There's our parent function. That's what we start with, y equals radical x. And now we want to apply a horizontal shift. Now, a horizontal shift takes the form y equals radical x minus h. That h there determines your horizontal shift. But horizontal transformations work opposite from the way you expect them to. In other words, x minus 3 would be a shift 3 units to the right. X plus 3 would be a shift 3 units to the left. Horizontal changes always work opposite the way you expect them to. Vertical changes usually work exactly as you expect them to. Okay, so when we were doing a vertical shift yesterday and we did plus 2, that moved it up. Okay, in this case, plus is going to move it to the left. So it's opposite with horizontal. Okay? So our first example is y equals radical x minus 4. So we know that we want to move it 4 units. The question is, which direction? So which direction should our graph go? To the right. 4 units. So all we have to do is take our parent function and move it to the right 4 units. Now if you want, we can make a table of that. But our table is going to look a little different than our table changes yesterday. Yesterday we were always changing our input. But now since we're doing a horizontal change, we're going to change our output. So think about this. Since we're shifting to the right, where would x equals 0 go? To 4. Where would 1 go? 5. I'm going to have 6, 7, 8, and so on. But we're not moving 6, or we're not moving 2. We're moving 4 right 4 units. That would put it at 8. And moving 9 right 4 units, put it at 13. Moving 6 right, or 16 right 4 units, we'll put it at 20. So basically we're taking our original x values up here and we're adding 4 to each of them. Now think about why that works. If you follow the equation down here, if we put in 4 for x, what's 4 minus 4?
0.
0. And what's the square root of 0?
0.
What's 5 minus 4? And what's the square root of 1? What's 8 minus 4? And what's the square root of 4? 13 minus 4.
9.
And the square root of 9? 20 minus 4. And the square root of 16?
4.
So notice that our y values are exactly the same. All of our x values are 4 more. That makes sense? We had to make this 4 so that when we plugged it in here, it would behave like this 0. Okay? So now all of our points are shifted 4 units to the right. What was 0, 0 is now 4, 0. What was 1, 1 is now 5, 1. What was 4, 2 is now 8, 2. 9, 3 becomes 13, 3. And 16, 4 becomes 24. Then we just draw our curve. It's not a vertical change at all. It looks like a vertical shrink because it's below the other one, but it's just because it's slid to the right. See, our graph is smaller over here than it is over here. So when we shift that small area to the right, it looks like a vertical shrink, but it's not.
So in these, there's no vertical change at all?
No, in this one, there was no vertical change at all because everything that changed under the radical. Okay? Changes underneath the radical here are horizontal changes. Changes outside the radical sign are vertical changes. Okay? Underneath the radical is horizontal. Outside the radical is vertical. Make sense? Let's do another one. Let's try y equals radical x plus 7. So if I was making a table, how would I change my values? Subtract 7 from each x, which is going to make it -7, -6, -3, 2, 9. And then our y values don't change because -7 plus 7 is 0, and the square root of 0 is 0. -6 plus 7 is 1, and the square root of 1 is 1. So everything works exact same way.
I have a question.
Yeah.
Could you just put in for the y 0, 1, 2, 3, 4, and then figure out the x's?
Why not? Okay. So then we can plot our points, which is every point that we already have shifted to the left 7 units. So 0, 0 becomes -7, 0. 1, 1 becomes -6, 1. 4, 2 becomes -3, 2. 9, 3 becomes 2, 3. 16, 4 becomes 9, 4.
So 7 units to the left.
7 units to the left. So again, this would look like a vertical stretch because it goes on top of the other one, but it's not actually a vertical change at all.
Why is it that if it's like x to 7, we subtract a 7 before we add it to the 7, and why is it when we
Why is it that the x ones work opposite?
Well, not why do they act opposite? Why do we take another, like, why do we not just do x to 7? Why do we subtract first and then that would be 14?
Because what I'm trying to do is I'm trying to get these x values to behave like these x values. And in order to get -7 to behave like 0, I have to add 7, right? And in order to get -6 to behave like 1, I need to add 7. Oh, sorry, -6 to behave like 1. So to get -3, I add 7. Okay? So I'm undoing what I have to do, right? Let's see. Let's look at it another way. It was 0, 1, 2, 3. Not 1, 2, 3. 1, 4, 9, 16. Now I want x plus 7 to fill in for my 0. And I want x plus 7 to fill in for my 1. And I want x plus 7 to fill in for my 4. Right? So if x plus 7 is going to fill in for 0, what does x have to be? And if x plus 7 is going to fill in for 1, what does x have to be? -6. And if x plus 7 is going to fill in for 4, what will x have to be? -3. That makes sense? It's different with y because y is an output, and so we're just changing our output by multiplying and adding. When we do our input, everything switches around.
So now when we do domain and range,
Yeah, so now our domain for our original function was
x is greater than or equal to 2, or x is less than or equal.
Well, no, it was always
no,
greater
can't
than
go the other way. and y was greater than or equal to 0, right? Now, when you apply a vertical shift, the y value, the range changes, right?
Yes.
When we apply a horizontal shift, what changes?
The domain.
The domain. What would our domain be for this function?
X is greater than or equal to
-7. And does the range change?
No, it's always the same.
It's not always the same,
Well,
but
for
when we're
this-
only applying horizontal shift, it only changes the domain. When we're only applying vertical changes, it only changes the range. Okay, because range is what outputs, what vertical values you cover. Domain is what horizontal values you cover. Make sense? Now let's combine them, but before we combine them, I'm going to give you the proper steps for applying the transformations we've learned so far. The first thing you do is a horizontal shift. Actually, I changed my mind. I'm going to apply these a little different. It's not a huge difference. You could do these either way, but we're going to follow what the book says in this case. We're going to apply the vertical stretch or shrink first. Along with the reflection, if there is one. Okay, so if there's a reflection over the x-axis, that goes along with our vertical stretch or shrink. Then we're going to do our horizontal shift. And our vertical shift. Now, your horizontal and vertical shift, you can actually kind of do them together. And you'll see what I mean when we graph this next one. Basically, you're going to figure out how far left or right and up and down it moves. And then you're just going to move the graph as a whole. So in example 5, we're given y equals 2 radical x plus 4 minus 1. Now, I'm actually going to graph this before we make the table. Okay? Because the graphing, if you have the parent function graphed, the graphing function is really easy to do. Or the stretch and the transformation is really easy to do. And then I'll show you kind of how the table ties in. So our first step, I'm just going to graph the points. So which part of the transformation are we supposed to do first?
what's in the radicals.
Nope. Check the order that I just gave you.
Oh, for the vertical stretch or shrink, and the reflection and horizontal shift.
Okay, so first the vertical stretch, shrink, reflection, which in this case, what is it?
2.
Is that a stretch, shrink? Is there a reflection?
Stretching.
It's a stretch by a factor of 2. And is there a reflection? No, because it's not negative. So we're going to stretch it by a factor of 2. Now remember, when we stretch everything by a factor of 2, it's like we multiply the y values by 2, right? 0 times 2 is still 0. That point doesn't move. But 1, 1 now goes to 1, 2. 4, 2 goes to 4, 4. 9, 3 goes to 9, 6. 16, 4 goes to 16, 8. Okay. Remember, before it was up 1 over 1, up 1 over 3, up 1 over 5. Now it's up 2 over 1, up 2 over 3, up 2 over 5. Make sense? So that's just our stretch. I'm not going to connect the dots because we're going to shift them. This is just kind of a reference mark before we do the shift. Everybody good so far?
Yeah.
So now we apply the horizontal shift and the vertical shift. What's the horizontal shift tell us to do?
Go left.
Left 4 units. You got the opposite part, right? But we got to make sure it's left because it's horizontal. And what's the vertical shift tell us to do?
Go down 1.
Down 1. So I could do it in 2 steps. I could go left 4 and then go down 1. Or you could just do it all as one step. Take every point, move it left 4 units, down 1 unit. So let's take each point, move it left 4 units, down 1 unit. Now, if you got copy and paste like me, you can be super, super fast. Look at that, I'm already done. So I took each of those points, moved. They might intersect once. Left 4, down 1, left 4, down 1, left 4, down 1, over and over and over again. Make sense? Okay with that? So that set is our final points, and I can connect those dots. Just make sure you might want to erase your intermediate step so that you're seeing which dots you got to connect properly.
That'd be really weird if you accidentally connected to the wrong one.
Okay. Make sense? Everybody good so far? Yeah. Now, a lot of times, it's easier to graph than it is to do the table. But let me show you how I would have done the table. If I had to make the table, I would make it applying the same transformations we've made so far. Okay? Before, it was 0, 1, 4, 9, 16. But now we're moving it to the left 4. So what's our first x value going to be? Negative 4. Because 0 minus 4 is negative 4. What's our next x value? Next x value? 0. Then?
Not 2.
No,
5. Next one? 12. So all I'm doing is I'm taking my x values up here, and I'm shifting them left 4 units. So I'm subtracting 4. It gives me negative 4, negative 3, 0, 5, 12. Make sense? Because the only thing that's going to affect my x's is the horizontal change. Now look at the points that I crossed here. That has an x value of negative 4, x value of negative 3, x value of 0, x value of 5, x value of 12.
so here both the domain and range are affected.
Yes, because we did both. We did a horizontal and a vertical, so it's going to affect the domain and the range. All right, now our y values, we did 2 transformations to them, right? Stretched them by 2, so we're going to multiply our y values by 2, and then we shifted them down by 1, so we're going to subtract 1. So where does 0 go? Negative 1. Where does 1 go? 1. Because 1 times 2 is 2, minus 1 is 1. I'm taking my original y values up here, and I'm stretching them by a factor of 2, and then subtracting 1. So I'm multiplying each y value by 2, and then subtracting 1. So 0 times 2 is 0, minus 1 is negative 1. 1 times 2 is 2, minus 1 is 1. Where does 2 go? 3. Where does 3 go?
Wait,
5. 3 times 2 is 6, minus 1 is 5. Where does 4 go?
7.
7. Okay, and you can check those will match up exactly with your points. So if you're making your table, you can do that the same way. Okay, if you really want to, you can plug in. You can start with the table, and you can plug in x values that will give you a perfect radical. You just got to look at what's underneath there. Since it's x plus 4, and my smallest number where the square root is 0, I'm going to need to plug in negative 4. Okay, and then I can go up by
I'm
odds.
glad we did this in 2 parts.
So this goes up by odds. It goes up by 1, 3, 5, 7, right? Because that's how squares go up. That's how our perfect squares go up. So the numbers that we're going to put into our square root, we want to go up by the same pattern. Okay, up by 1, up by 3, up by 5, up by 7, and so on. So what would be the next x value that we'd put in there if we were making a bigger table?
9. Oh, not 9. Sorry.
Okay, well, 6 is 25, which
21.
21.
Because you add 9 to 12.
Yeah. See, we're adding 1, 3, 5, 7, 9.
I
Okay.
was doing the whole thing.
Oh, you were working backwards from 25 down.
Yep.
Okay. Okay. and then it would be 32 and so on because we're just going up by odd numbers. Make sense? All right. Any questions? All right.
I'm glad we